All right, you're ready to go.
Yeah, thank you, Ray. Thank you for the invitation, as I was saying, and thank you all for being here. So today I'm gonna explain to you what's TornadoVM. So you haven't heard about it, you are in the right talk. So I will explain the basics. And my goal today is just to let you know what it is and how you can start using it. So before I dig into TornadoVM, I would like to start by motivating why we're doing this project. From my view, why we need something like TornadoVM. So, heterogeneous hardware now are everywhere. So smartphones, my laptop has 2 GPUs, data center has GPUs and FPGAs per node. So it's pretty much at every scale: smartphone, tablets, laptops, data centers, servers, and so on and so forth, you name it. The thing is, hardware is great because we can run workloads more efficiently, meaning or either faster execution times or with decreasing energy consumption, and that's great. But we need a way to program this hardware. So for now, if we take a GPU, for example, the mainstream programming models could be something like CUDA, OpenCL, or oneAPI, or maybe something on top of these models, right? But mainly those models are based on C and C++. And we see that not every developer is a C++ developer. If you look at the ranking, you will see many developers using JavaScript, Python, R, Ruby, Java, and so on and so forth. So how can we enable heterogeneous execution for those languages? Well, there are some strategies. I will talk about those in a bit. But essentially, TornadoVM fits into this place. So basically, it's an alternative to run, to offload Java programs to run in a transparent manner, to accelerate on GPUs, FPGAs, multi-core, or any other compatible accelerator. That's what we do. So before that, well, it's the first time I show in this group. So just to a few words about myself. So I'm a research fellow at the University of Manchester. Mainly what we do is research in the virtual machines and heterogeneous computing part, programming models for heterogeneous computing, and so on. I'm one of the architects and the main developer of the TornadoVM project. I'm also involved in what is called Intel oneAPI Innovator, basically. I'm involved in several things. One is the oneAPI language group. And the other one, I'm not that too involved in that group. It's just recently I joined. And the one I'm most involved with is the hardware group, which is essentially the level 0 specification for heterogeneous hardware within Intel. So what I want to cover today is how we can access heterogeneous hardware from Java without TornadoVM. So what is around today, and the need to have something like TornadoVM. And then I will explain a general overview of the project, and then I would like to highlight the key features of TornadoVM. TornadoVM has many features, so I would like to highlight the most important ones. I will show you also a demo. So as I say at the beginning, I would like to trigger this more like a discussion. So if you have questions for me, there is no problem. So feel free to interrupt and we can address those comments. I'm actually keen for getting your feedback. So if you are here, that means that you are interested in the topic or you are an expert on this topic. So I'm interested in getting your feedback and your comments. So yeah, don't be shy. So let's motivate how is the landscape for the Java ecosystem. I talk about Java, but could be any other managed runtime system, a managed runtime environment, for example, .NET, Python, JavaScript, etc. So if you want to run on heterogeneous hardware right now, either you can use an external library, so the vendor, let's say NVIDIA or Intel or AMD or whatever other vendor gives you a set of pre-built functions, let's say for deep learning, and you can use them, that's fine. Or an alternative is to have like a wrapper. So essentially it's like having a way to implement your OpenCL, CUDA, oneAPI program from high-level programming models like Java. So in my view, that's fine. I mean, developers are used to it, and that's fine. We believe in another alternative. The main drawbacks of this is that you rely on a specific set of functions that the vendor gives you. Okay. If you want more, you need to ask for more, or you need to, in the case of a wrapper, you need to implement your functions and break models. Let's say you are using Java, but then you need to implement your algorithms in something that is not Java and doesn't follow the Java programming, the execution model at least. Right, so if you take Java, what the Java virtual machine does is that as soon as the code runs frequently, usually it's at the method level, so at the function level, the Java virtual machine invokes the just-in-time compiler. And the just-in-time compiler will compile to efficient machine code for the CPU. But this doesn't exist for heterogeneous hardware. So if you want something similar, there is nothing around. And that's what TornadoVM comes into place. So TornadoVM is not a new VM by itself. It's a plugin. So it needs Java, JVM. So it's like a complement for execution on heterogeneous hardware. It complements OpenJDK. We can use OpenJDK-based distributions like Amazon Corretto, Red Hat Mandrel, Windows JDK, and also GraalVM. And what these VMs do essentially is that, as I mentioned at the beginning, is that they compile methods to efficient CPU, right? Efficient CPU code. With Tornado, we complement and we can access in the same way to multiple hardware like GPUs, FPGAs, multi-core systems, RISC-V accelerators recently, and so on and so forth. So we focus on Java for the talk, but I will show you a demo running JavaScript, so with Tornado. So you can use JavaScript with GraalVM. There is a plugin to do so. I will show you an example later on. But essentially what we do is at the TornadoVM level, it has compilers and runtimes to access what is a lower level. And right now we have 3 backends. We have a CUDA backend, an OpenCL-C backend, and the new one in combination with Intel. We're working with Intel with this for this port for SpeedV, and it's dispatched through level 0. Right. So I have. Okay, don't worry. There are many names in this intro. In the rest of the presentation, I will show you step by step how it's done. Right. So let's get into this, and I would like to show you first an example. So yeah, I would like to show you the caramel, and then if you're interested, you will see how it's implemented. So this example is open source. You can read the code. It's online. It's in this URL in GitHub. And essentially what it does is a blur filter. So it's a typical example in computational photography. I think it's widely used today because this fancy background, blur effect in the background, Zoom uses it, and well, Google uses it, and so on. So basically, you have a picture, and you want to blur some sections of the picture. So I'm going to jump to the terminal, and I'm going to show you. Hopefully, you can see the terminal. Give me a signal. Yeah? Hopefully, yes. I'm sharing the whole screen. So I'm going to show you what Tornado has available. So this command is tornado//devices will give me the devices, the accelerator that Tornado can see. I'm running this on my laptop. So here it's telling me that there are 3 drivers. Drivers in TornadoVM means backends. So it has the SpeedV backend, the OpenCL backend, and the PTX backend. And within each backend, you will see different number of devices. So for the SpeedV backend, we have 1 accessible, is SpeedV through the level 0 API. For OpenCL, we can dispatch code through the OpenCL runtime available for NVIDIA GPUs, and for Intel integrated graphics, and for Intel CPUs. I want to say that this device, the Intel integrated graphics, is exactly the same as this one. The thing is, it's reachable from different implementations, right? One is level 0, and the other one is OpenCL. By the way, in theory, they should give us the same performance. I will tell you, I will show you an example about this, that this is not the case. So depending on the backend that you are using, we can get better or worse performance. And the last backend is the PTX backend. So PTX is the intermediate code for CUDA programs. And as you know, CUDA is proprietary from NVIDIA, and we only can run on NVIDIA GPUs. I think there are external work around this area as well to port CUDA to other devices like Intel, etc. I saw it this morning, actually. Right. So what I want to mention here is that I want to run on these devices. I'm gonna use this one. This one is the default. You will see a number. Is device 00 means backend 0, device index 0. Backend 1, in this case, is OpenCL. Device index 0 is the NVIDIA GPU, and so on and so forth. So depending on your installation or your system, you will see different reordering. So this is what applies to my machine. But if you install Tornado, you will see different reordering. So let's jump to the application that I show you, the blue filter. I'm gonna start by running, hopefully you can see the terminal, text, the multi-thread application. So this application, although I'm running with the TornadoVM command, I'm passing a flag for this application that says, don't go through Tornado, just enable Java threads, okay, multi-threads. And I'm gonna run it. This is running.
Hi, sorry to interrupt you. We cannot see your updates.
Can you see the terminal? You cannot see the terminal.
We only see the slides named example blue filter. Let's run it.
Okay, sorry. Okay, I'm gonna stop sharing and I'm gonna share again. I thought I shared the whole screen. Window. Now, can you see the terminal?
Yes, I can see.
Yes. Okay. So let me do a recap just in case. Yes. To show you the device number. So I was explaining this. Yeah. So if I run Tornado's last devices, we'll see a different set of devices. So in fact, we have 3 different backends: PV backend, the OpenCL backend, and the PTX backend. So what is here is Tornado drivers is a synonym of driver, right? Backend. And within each backend, we will see different number of devices. So SPV has access to the Intel integrated graphics through the level 0 API. The OpenCL backend has access to the NVIDIA GPU that I have here in my laptop, the Intel integrated graphics, and so on and so forth. And I was mentioning that each device is identified uniquely in Tornado by device with 2 numbers. So the first number is backend : device index. So backend 0 device index is this one. 00 is this one, 10 is this one, and so on and so forth. And I was saying that if you install Tornado, depending on your configuration, on your installation, you will see different reordering. But essentially, Tornado gives you this utility to check the device number. And I was running in the second terminal. This application is the Java thread. Okay, it's a blur filter. Essentially, this program that creates a blur effect over an image is 5,000 pixels by 4,000 pixels. And I run it multiple times here. Well, you can see the trace. I run it multiple iterations. It's taking around 11 seconds, going down 10 seconds. Don't take this as a full benchmark. It's just to give you an idea how the speedups you can get. We will see similar numbers. I'm going to stop it now. And I'm going to enable Tornado now. So if I run with Tornado, it's the image preparation, and then it's running. You will see that in a bit, you get the timer. It's going down to 4 seconds, right? 3.6 seconds. And I have this flag called thread info, which is an internal flag in Tornado that will tell me in which device the application is running. So remember, when I run the multi-thread with the thread info, didn't speed anything, didn't print anything because I'm running with Java. Now I'm running with Tornado, and it's taking, because I don't pass any other information, it's taking the default device. Remember that if I go back to the list, the default is 00, is SPV with level 0 on the Intel integrated graphics. And it's exactly this one. And that's the dimensions of the picture, essentially, and the number of the block of threads to be deployed for this example. And I can, let's say, change device. Well, before changing the device, I want to show you that you can also see the kernel that we generate, so Tornado generates. In this case, we're using SPV, so the code that is generated is SPV. I'm not going to go through it, so it's very ugly, but you can get the idea, right? So Tornado automatically will generate this for you. You can see the code. Even you can modify if you want to. We provide tools to do these kind of things. So let's change the device. I'm going to stop this application. And let's use now device, let's say 1.0, right? So 1.0, let's go back to the list, is the NVIDIA GPU, right? I'm gonna keep the flags print kernel and print threads to trace where the application is running. So if I run it, now you will see a lot of code. So you see, we go now through the OpenCL. So it speaks OpenCL C code, essentially. And we will see all the tasks running, and the time goes down to less than a second. In fact, 0.3 seconds, right? So remember, the multi-thread was around 10 seconds, 9 seconds. The integrated GPU was around 3 seconds, and then with NVIDIA GPU goes down to 0.3 seconds. If I have an Arc GPU, Intel Arc GPU plugin here, I don't have it in the laptop, but in the future we might have it. You will see also accessible from OpenCL, either OpenCL or SPV. So hopefully this gives you an idea of the speedups that you can get. And the application is fully written in Java. There is nothing related to any function call, any foreign function call to CUDA code, OpenCL code, SPV. It's just Java, okay? So if I print, if I plot the speedups for this application on my laptop, I get this. So this is a comparison against Java sequential. And I compare it with Java sequential because the code, the initial code that the programmer writes is sequential, right? So as a programmer, as a Tornado programmer, you write usually Java sequential code, and Tornado will automatically parallelize it. We have tools and API to instruct the compiler how to do so, and I will show you in a bit. So we can run on many devices with different backends. So if we run with the OpenCL backend on NVIDIA GPU, we can get up to 430x performance, which is quite high. Even the Java even this on the CPU, we can also get really nice speedups. This one, the third bar, 20x, is by using Java, by offloading to OpenCL and using the CPU, okay? In this case, we'll use the vector instructions on the CPU. If we compare against Java multi-threaded, which is the maximum performance you can get with Java without using external libraries, we see a performance benefit of up to 30x, which is quite good, right? So I hope I show you, sorry, actually, I wasn't sharing the right thing. Just a second. Yeah. It's funny because I share the whole window, but it only allows me to share the actual. I mean, I share the whole screen, but we only see the window anyway. So yes, that's the performance I was talking about, and this is the comparison with multi-threaded. So it's up to 30x times faster compared to 16 Java threads. It's an 8-core machine with 2 threads for each core. So yeah, the speedups are considerably high for automatic parallelization, essentially. So, okay, I'm gonna start now going deep. I'm gonna show you how this is done. So Tornado is open source. It's available on GitHub. You can download the code. You can see the code, etc. We have a website where we have presentations. We have documentation as well. We have tutorials. And as I said, Tornado is just a Java framework, just to recap, a Java framework that allows us to offload a subset of Java to accelerate on heterogeneous hardware. And we can use any OpenJDK-based distribution. We can use Azure Systems, Zulu JDK, OpenJDK, GraalVM as well, Amazon, Corretto, Red Hat distribution, which is a fork of GraalVM, and Windows JDK. Probably more, but we have checked these JDK distributions. Some key features of TornadoVM is that it allows us to do dynamic reconfiguration or dynamic task migration. This means that TornadoVM not only offload code, right, to run on the target hardware, but can also do a migration across devices during runtime. which is really cool. Let's say you have application running on one GPU, and then that suddenly Tornado switches to another device. Could be another GPU, or could be an FPGA, or could be a CPU, multi-core CPU. You can use TornadoVM to deploy on the cloud. In fact, we are using this for one of the projects we're running, Amazon Web Services, and we're using G5G instance with an ARM-based plus a powerful NVIDIA GPU. I think it's called T4 GPU. It also allows to run on multiple devices and multiple backends. Well, I show you this in the examples. And one of the key features of Tornado is that the API is hardware agnostic. I will show you now an example. And that means that we don't do, so as a developer, you don't specify anything related to the actual hardware. It's fully agnostic. So for us, we deal as a device. Now, if the device is a GPU or it's a FPGA or it's a multi-core, that's the work of TornadoVM, how to offload and how to communicate with the corresponding drivers, essentially. And it also has a specialized JIT compiler. So the JIT compilation, okay, the code that is generated is different depending on the device. This is because these models that we target underneath, let's say OpenCL is an standard that you can run on many devices. So the source code is portable, let's say, but performance is not portable. So that means that we need somehow to massage the code, right, in order to improve performance. And we do quite a lot, especially on the FPGA part. Right. So let's go down a bit, and I'm going to show you now the software stack of Tornado. So at the very high level, and that's what developers need to know, is that Tornado exposes an API. So Tornado does not exploit, does not auto-parallelize the application. It uses information from the developer, okay, that is used directly in the code to parallelize the application. So there are three main components, I will say. We have annotations. Actually, we have two annotations, add parallel and add reduce. So if you're familiarized with oneAPI or oneACC, this is something similar. So we annotate at the loop level. And we annotate parallel loops and parallel reductions. That's one thing. The second thing is we create a task graph. Each graph each node in that graph is a method. It's a Java method. It's a function, right? And that means that Tornado offloads code at the method level. This is the same as Java Hotspot, for example, OpenJDK, and so on and so forth. But with the task graph, we can say, combine all these methods in one single compilation unit and send it to the target device, which is really cool. So we can say offload 3 methods. That's the actual example I show you. I didn't go into the details of how it is the computational photography blur filter is implemented. But essentially, if you see the code on GitHub, you will see that there are 3 tasks in the task graph, 1 per channel, RGB. So when it's an image, we can split it in channels, red channel, blue channel, green channel. Each channel is a task. And we compile all these tasks, the 3 of them, in one single compilation unit and accelerate it on a GPU or any other compatible device. So the task graph can be seen as a definition of what we want to offload. Let's say this code with this data. It's a definition. And then we have another data structure. It's called execution plan. And the execution plan essentially is a way to pass parameters and optimization values to the actual runtime. The optimization values are optional, though. But if you want to, pass your own set of grid, for example, a block of threads or enable the profiler, these kind of things, you can do it through an execution plan. And this is everything that developers need to know. It's a lightweight API. Yeah, I believe it's not too overloaded. So it's easy, or should be kind of easy to get the philosophy of what we follow for this API. But yeah, that's the information that we have to get in order to offload the application. So that's at the API level. The rest is pure runtime. I'm going to show you very quickly, but as a developer, you only care about the API. So in the runtime, what we do is that we build a data flow graph. This data flow is based on the task graph. And we build this data flow in order to optimize memory transfer, mainly. Why is this? Because you probably know that discrete GPUs, especially, and discrete FPGAs, don't share memory with the main CPU. So that means that the data needs to be pre-allocated, and data has to be sent back and forth before and after the execution. Those data transfers are usually done through PCI Express, and this takes time. If we can save data transfer, we can speed up the overall process, right? Not just a single task, but the whole computation. And that's the goal of the data flow analyzer and optimizer. So essentially, it will build a data flow graph with all the dependencies and will say, this one, you are not using temporarily, so you don't need to copy data or copy out data. It can remain on the GPU, things like that. From that graph, we optimize it, and then we generate our own intermediate representation. It's called the TornadoVM bytecode. I'm not going to expand too much on this, apart from this slide. Essentially, the interpreter is a way to orchestrate the execution. Right? We have actions to allocate data automatically, to send data, to add barriers, to launch kernels, and to compile tasks. One of these bytecodes is compile, essentially. And the first time we see a task, we offload the Java bytecode that represents that method to the target backend. Let's say, in this case, SPV. So we offload the Java bytecode representation for a specific method, and we optimize it and offload it to SPV binary. Then the TornadoVM runtime will cache the final binary, and if the whole execution is relaunched, we just get the binary from the code cache that we have, essentially. So those are many terms. Hopefully, during the rest of the presentation, it will be more clear. Unless you have questions, I'm going to continue. So let's expand on the API. And I believe this is important because if you want to use Tornado, it's important to understand this API. I briefly explained the API at the very beginning, so before in the previous slide. And now I'm going to expand on the three main areas, which is the annotation, the task graph, and the execution plan. So we ask ourselves a set of questions when we build this API. First of all, how do we represent parallelism? So Java was not designed for GPU programming in mind from the beginning, and we need a way to. It's like a trade-off, right? We need a way to get that information somehow, but not create an overload set of API or parameters, etc., because otherwise it will be harder to use. So it's always a trade-off. So how to represent parallelism in Tornado, we thought about two ways. First of all, through the Java annotations that I explained briefly in the previous slide, we have two, add parallel and add reduce, and the intention is to annotate loops within methods, right? And the actual code that you annotate is Java sequential code. Again, it's not full Java, it's a subset of Java. And there is a second way, those are complementary. So instead of using annotation, you can use what we call a kernel API. And if you're familiarized with CUDA or OpenCL or oneAPI already, this API, the kernel API, will look very familiar to you because it's very close to how you express kernels on those programming models. So why we have this API? Because some developers ask, they knew OpenCL or CUDA already, and they have existing code on those programming models already. So they want a way to easily port this to Java and TornadoVM. Why do you want to do that? Because it's not about just the execution of the kernel. With Tornado, you get more things. You get automatic memory management, you get task migration, you get batch processing, I will explain later, and so on and so forth, right? It's not just about the kernel itself, it's a set of tools around it that you don't have to code by yourself because Tornado will take care of it. So this is how we represent parallelization. Then the second question we ask is how we know the methods to accelerate. So imagine that you have a big project in Java. You have many classes, many methods. Which ones should be used to offload? So for that, we build a task graph. And as I mentioned, the task graph is just an API to define code and data to be offloaded. We can have many tasks from different classes, essentially. And that's the definition, right? And then how we run it. We run it through an execution plan. And let me show you an example now. I took the typical matrix multiplication. Is now, as you know, what they use in deep learning now. This is the canonical example. And this is a Java class called compute that has a single Java method called mxm. And we pass 3 matrices, A, B, and C. Those are Java types that we provide to the user. And the final is the size. It is optional because we can get it from one of these objects. But just to make it clear. So this is the sequential Java code. So let's start using the annotation part, okay, the annotation API. So in the matrix multiplication, the first 2 loops can be parallelizable. There are no data dependencies between them. So we can add the annotation at parallel, right? So we have identified where the parallelism could be located, and we put the annotation in there. This could be optimized further, but for now, we have up to this level of optimization with this API. If you want to use the kernel API instead, okay, to identify parallelization, you can use it, and the kernel will look like this. And if you know CUDA, this is pretty much, or OpenCL or oneAPI, this is pretty much one-to-one mapping. We have a new object that Tornado provides. It's called kernel context. And through the context, we can access the thread IDs in the X dimension, in the Y dimension, for example. Right. So that's the identification of parallelization. And then we need to build the task graph. How do we do that? Well, we have a data structure called task graph. We pass a name, could be any name, because if you want, during runtime, you can refer to those names and perform some actions. For example, enable profiler or change device for this task and so on, right? But it's optional. And the task graph API, inside we have actually 3 main methods. It's very lightweight API. So we have transfer to device, transfer to host, and tasks. The transfer to device defines the data to be sent from the Java heap to the device memory. Remember that these accelerators might not share the same memory, so we need to identify which data to be sent. Right? In this case, we call transfer to device, and we say transfer metrics A and B, which are inputs. Then transfer to host the result, which is we're expecting the result in matrix C. So if we take a look, matrix A and B is the actual input data, and C is the output. Right, and in between, we can have one or many tasks. Yep, we have a question.
Yeah, I think in earlier slides, I saw that, the performance optimization is dynamic depending on the type of device encountered.
Yeah.
If you're tagging here if you're using annotations, the runtime optimizations to offload to accelerators may not be that much. And unlike, say, LLVM or something, right? Do you have a roadmap to not use annotations? Or
yeah, okay. So, that's an excellent question. Indeed, some years ago, we thought about removing the annotation completely. I think we can manage because we have our own data flow analyzer. I think for some cases we can manage. And Java is not like C, so we don't have this aliasing stuff that is present in C or C++. So still, we can get some code running. However, after we talked to Oracle, they recommend us to keep it. Why? Because in Java, it's well-defined, and when you have a set of operations, they know the precision of that operation. By introducing at parallel, the programmer is conscious, let's say, that the code might not run exactly as the Java specification says. Does that make sense? So yeah. It's like a hint that say, hey, look, be careful because you have a notation. If you're expecting the same precision as the Java specification says, or the Java semantic says, This is not what they're going to get. So they recommend us to keep those annotations.
Got it. So if I need to use, say, CURAs or some libraries, will it run as though I'm running CUDA, or will Java style take over?
Yeah, I'm not sure I got your question. So you're asking for some data structures between Java and CUDA?
Yeah, the, CURAs or QRAs, or how do you say it? I don't know, you use CURAs or GPU array?
Yes, so you can, okay. You can use standard Java arrays like int array, float array, and so on. Or you can also use the types that Tornado offers. In this case, it's matrix to the float, for example. One thing, we're changing this. Okay, this is as if you download Tornado today, but we're working towards, I think we're going to deprecate all primitive arrays in Java and use only the types we offer. And the reason is that if we have int array or float array as Java, plain Java, we have to do a copy between the Java heap and then the native heap, and then we might have another copy between the native heap and the actual device memory. So we have an extra level of copies, if you like. So what we are working on right now is to, you know, if you're familiarized with Panama API in Java, essentially it's a way to access native memory. And with Panama, we can use pin memory, we can use share memory, etc. So those data structures will be pin or share, etc. And we can speed up the overall execution.
Got it. Okay. No, thank you. And I read context aware, so I wanted to make sure I get the array part right.
Yeah, absolutely.
So,
yeah.
Thank you.
Yes. And the task will tell us in between, we can have one or many. In this case, I'll show you one, but we can have many tasks, as I mentioned. It's basically a name for the task and then a function, a method reference, a function pointer. This is a lambda expression, essentially. And then the data involved in that function call. That's all. It's pretty easy. So from there, we have the definition, and then we need to execute. To execute, we create what we call an immutable task graph. This is on purpose because still the user, accidentally or not, can modify, in theory, the task graph. Let's say adding more data or adding more tasks while the GPU is already running. We want to prevent this situation, so we create what we call a snapshot, and then we pass the state to an immutable task graph. Through that immutable task graph, we can create an execution plan, and the execution plan can have one immutable task graph or many. In this case, it's just one. And through that, we can call functions like perform a warmup, enable the profiler, enable dynamic reconfiguration. Remember that this dynamic reconfiguration is the ability of Tornado by itself migrate tasks across devices, and so on and so forth. This is optional. So you can say execution plan.execute directly, and Tornado will have the default device, the default behavior, etc. And after the execution, you will get an object type called Tornado execution result, and through that, you can query, for example, the profiler. So I want to mention that the task graph doesn't execute anything. This is just a definition. The time we call execute over here is the time that Tornado will offload the code, okay, optimize the code, and run on the accelerator. Right. This is a blocking call. It's a synchronous call, but we are working on an async version, if you like. But that's work in progress. Okay, so hopefully this is clear, but feel free to ask. We have an extensive documentation in our website. Read the docs with how to install Tornado, with examples. We explain step by step the execution plans, the task graph, and so on. And also in the repo, the main repo of the project, we have a set of benchmarks, examples, and unit tests that you can take a look at if you want. Right. So let's switch now to the runtime. a bit going down. Actually, I'm gonna jump to the Git compiler instead of the runtime.
There was
With the
there was a
question.
question. Yeah, there was a
Yeah, go ahead.
question by Jakob. Said, can the task graph be reused between calls?
So you want to share the task graph with different execution plans? Yes, I think yes. Well, essentially, you create an immutable task graph, and then that immutable task graph can be used for different execution plans. Yes.
Okay, so if I need to repeat the same set of operations but on a new set of data, then I don't need to recreate the entire task graph again and create an execution plan for it. I could just use the existing execution plan and add some new data to that.
Right. So the data is attached to the task graph. What you could do is to have a different task graph with different data, and the two can communicate. We have an example of this in the repo. Yeah. Is that featuring? So in a sense, a task graph has the data associated with it. The reason we do this is because we do aggressive optimization, and we do what is called a sort of parsing evaluation. We get the data sizes and so on to optimize further for the GPU or for the FPGA. I don't know if I answered your question, Jacob, but feel free to rephrase it if you want.
It's clear enough. It's clear
Okay.
enough. I will bug you another day with the with the details.
That's fine. Okay. So let's continue. I want to talk about the decompilation just for a bit. This is getting low level, but yeah, I'm gonna go quickly over here. So let's say we have a web program. In this case, it's a Java method, annotated Java method. Okay, it's just about the method. Remember, we also need a task graph and execution plan. For simplification, I just put the method because it's actual code to be offloaded. And there's no modification in the Java C compiler. It's just Java C. So we transform from source to intermediate representation in Java bytecode. And from there, at runtime, we get the bytecode that represents this method and build a graph. We base on Graal. Graal is a new, well, it's not that new now, but yeah. It's a new Graal, it's a new Java compiler written in Java for Java. Okay, it used to be in Oracle Labs, so it used to be a research project. Now it's in production. And Graal has its own intermediate representation. It's called Graal IR. It's in a graph form. And in the graph contains data flow and control flow in the same graph. What in Java is called, or in the compiler literature, is called sea of nodes. Right, so what we did was to extend Graal for compiling code to different accelerators, CUDA, OpenCL, and SPV. So from the Graal IR, we basically transform the IR to have a common IR for accelerators. In here, for example, we do no replacement. Let's say, we have a parallel annotation on a loop. Let's replace that loop and introduce the equivalent to a thread ID, which is close enough between them, between CUDA, OpenCL, or oneAPI. We also have more optimization, for example, to identify reductions that we do automatically, and so on. From there, we specialize the IR depending on the target backend. So we have an IR for PTX, an IR for OpenCL, an IR for SPV. And in the IR, we have many compilation phases. Indeed, we not only pass compilation phases related to the accelerator, we combine existing Java compilation phases like loop unrolling, for example. Sometimes we have to tune it, especially for FPGAs, but those are corner cases. Loop unrolling, constant propagation, this kind of thing, we reuse it. So this is a key differentiation between other projects. So in Tornado, we interleave well-known compiler optimizations that are provided by Graal with our own compiler optimizations in the pipeline. So in total, we will have, well, I haven't counted, but close to 100 optimizations that we pass. Once the code is optimized, it's in the graph form still, we traverse that graph, the optimized graph, and generate the corresponding code. For example, if we target PTX, we generate PTX assembly code. If we are targeting SPV, we generate the binary for SPV, and so on. Right. So in the case of SPV with Intel, it's a bit different because we also decouple the internal tools, and you can use it if you want to. One of the tools is Beehive SPV Toolkit. It's essentially a Java API that you can use to build SPV kernels in Java, right? It's the API that we use internally to go from the Graal IR to SPV. But as I say, we decouple completely and other people can use it. One of the things I want to mention is that we focus on SPV for compute, but it's the same representation for graphics. So if you know Vulkan, for example, Vulkan share representation with SPV, meaning that you can use that library to generate graphics in Java, which is cool. I mean, I would like to do it. I don't have the time, unfortunately, but it's something like, it could be really cool. Right, so I'm not gonna spend too much time on the library, but essentially it's open source. You can download it, you can play with it. So I want to show you an example of the usage of this API, this SPV Toolkit. Let's say you want to do an operation, an addition, okay? So what you do is to request an ID. This is because SPV is SSA representation. So we get unique IDs per kind of sentence, if you like, per variable or per operation. So we request an ID and we say add to the current scope, could be, you know, a function scope, or could be an if condition scope, and so on and so forth. The current scope, add an operation, and the operation is SPV op IDD. If you don't know SPV, it might look like a bit ugly. However, it's one-to-one mapping between the spec and the Java code, meaning that for us it was easy because let's say I want to do the addition. What do we need for the addition? Which parameters? I go to the spec and tells me you need these 4 parameters. That's exactly what I put over here. So it's easy to, once you know what to do, to start adding the operands, right? And this will generate the code that is on the right-hand side. I mean, we disassembly it and we get this code. And so on and so forth, right? Well, the load operation is a bit more complex, but you get the idea. So we didn't only release the SPV Toolkit, we also released as a standalone library Level 0 API, the implementation for Java. We call it Level 0 JNI, which means that you could use this library for your own projects. So as again, it's fully decoupled from Java, or from Tornado, sorry. It's fully decoupled from Tornado, and you can use it for your own projects. Level 0, I don't know if you are familiarized, but it's essentially same level, but a bit lower level of OpenCL, right? You request a driver, you can manage memory, synchronization, you can have your queues for running kernels, and so on and so forth. You can access even the firmware. You can access even the frequency of the GPU. It's very low level. It's kind of the same as CUDA driver API. I think they're in the same level of abstraction. Yeah, but if you want to use it for your projects, you can use it. It's also open source and available on GitHub. Yes. So let's talk about key features of TornadoVM if we have time. And one of the features is the ability to run dynamic programming languages, not just Java, but other programming languages. For example, Python or JavaScript. In fact, what we do is to have the code expressed with Java and Tornado and invoke it from an implementation for Graal VM, a language implementation for Graal VM, like, for example, JavaScript. This is possible because Graal VM has what is called the truffle framework that allow us to implement programming languages on top of the Graal VM JIT compiler. Because everything is in Java, we can invoke transparently Java code. I ran an example today just to show you. Well, we have documentation about how to reproduce it, but essentially I took the JavaScript implementation, and in Tornado you can use this flag called truffle, -truffle JavaScript, and your program in JavaScript. And in this case, I'm using the SPV backend that runs a multiplication that is invoked via JavaScript, which is cool. You can even run on Node.js, for example. We have demos online that you can watch about running Node.js on a server and giving the client the output of a computation that was done on a GPU, for example. That's really cool. Right. Though very briefly, I'm going to sum up some of the key features. I talk about the task migration. Task migration means that Tornado can dynamically, migrate the execution context from one device to another. And could be any device. Could be one CPU to an GPU, once from a GPU to an FPGA, or from one GPU to another one, back and forth. So the way it's implemented is as follows. So Tornado internally spawns a set of threads. How many threads depends on how many devices you have on your computing setup. Plus, we have one thread to run the sequential implementations as it was in Tornado on that platform. Because what we want to do is to switch to the device only if we can guarantee some performance. Otherwise, Tornado will stay on the CPU. And that's one of the key ideas I want to to highlight today. So Tornado is not a replacement of Java. Not everything can fit on a GPU. Not every problem can run efficiently on a GPU. Some problems run very efficiently on CPUs, right? So in that case, Tornado will stay on the CPU. Only when the TornadoVM detects, you might run faster on this GPU, let's say, then the TornadoVM runtime switches context to that GPU and continues the execution. If you are interested, we have a paper on this topic. I thought I put it here. Well, ping me if you want that paper. I can send you the details. Another thing we could do with Tornado is batch processing. So GPUs usually don't have the same amount of memory than CPU have. So what we do is to kind of split the iteration space in smaller chunks, smaller batches, and process independently on the GPU. And we have two options. We have a sequential one, and we have a parallel one. The sequential implementation of batch processing is already upstream, so you can use it. And the way you use it is with the execution plan, you say with batch, and then you pass a size, let's say 300 megabytes, or 1 gigabyte, or 10 gigabytes, whatever you have available on the GPU. And we have a second mode in which we have different command queues, let's say underneath, and each command queue is doing a batch, right? And this can give us an extra speed up. We have to work on it, on this area. I think we saw something like 2x, 2.5x performance by running multiple queues, two to three queues. This is not upstream, but we're working to put it upstream. Another thing we could do in Tornado is not upstream, but we're working on it. Hopefully next release will be July. It's done. So we can, if we have multiple tasks in a task graph, and those tasks are independent each other, there's no dependencies between tasks, we could potentially run every task in a separate device as soon as you have multiple devices in your system. And that's what we call multiple device execution. And that could give you extra speed up. Again, this is done transparently. So if you have multiple GPUs, Tornado will do the job. Okay, we are finishing this work. It's already working. We will need to clean up a bit, and it will be published next month. Since Tornado is also a Java project, we can integrate it with all the Java projects, right? In this case, we did it for Flink. So Flink, if you're familiarized with Flink, is a big data platform for data streaming. And Flink, the architecture of Flink has one main server. It's called the job manager, with all the orchestration of the execution, and what is called the task manager. And the task manager is what the job is done. And we thought, okay, what if the task managers have GPUs or any other accelerators underneath? Can we use Tornado? So what we did was we plug in Tornado, and we managed to run and modify Flink programs On a GPU cluster. Well, not only GPUs, also FPGAs, right? And that's by the way, that's the outcome of one of our students, Maria Sekalaki, that she published the PhD, and we also have a paper in BLDV this year, so you can get all details from there as well. And just to give an idea about the speedups we got for this project, this is Flink with many different configurations. So the x-axis shows data size, y-axis shows speedup, and each bar shows a different configuration with Flink. 1 Flink node, 2 Flink nodes, and so on and so forth. So this one we run on FPGA, an Intel FPGA, and we go up to 180x compared to Flink, okay, which is quite good. It wasn't easy. All the details are in the paper why it wasn't easy, but yes, some speedups are possible. So I think I kind of ran out of time, so I would like to conclude. Tornado can be used not just for computational photography. You can use it for many things, right? We have examples for accelerating natural language processing kernels like k-means, Lagrange time function, and so on. IoT type of applications, digital signal processing. This is actually good even for FPGAs because we can use the pre-built part of the chip, okay, part of the FPGA to do this type of tasks. Also for physics simulation, fintech, and so on and so forth. So we have a lot of use cases. You can visit this website, tornadovm.org/use cases, and we have some of them explain step by step how we achieve this. We are running, so TornadoVM is not just program in isolation. We're running different projects. In fact, we're running now 6 projects. I've put here 3 of them. But yeah, you can get the idea. So one of the projects is called Aero. It's the latest we're running, and Elegant as well. And in this, we basically partner with companies like Red Hat or Codeplay from Intel, UBTech, CPER, etc., to run on RISC-V accelerators, for example. And also the Elegant, in which we accelerate streaming applications for big data. We also partner with, well, it's actually part of the Aero project, with one of the company that runs the ESA project. Part of the ESA is called the Gaia project, in which we analyze a set of spectrums in space with Tornado. We're trying to do this type of things. So with that, I would like to conclude. Just a few key sentences just to to close. So Tornado, in my view, we need something like this because we see more and more hardware coming, and we need a way to program those devices efficiently. One way could be through TornadoVM. I show you that TornadoVM has multiple backends that can be used to program different applications and to deploy on different systems. I show you very briefly key features of Tornado, like task migration or batch processing or multi-backend. Some of them are still ongoing, and some of them will appear in the next release. And hope I convince you that with Tornado, we can get high speed ups compared to standard JVMs. With that, I would like to conclude, and yeah, I'm happy to take more questions if you have.
Yeah, there's a couple of questions in the comments, and a lot of them are oneAPI based, like I guess around TornadoVM's relationship with Level 0 Toolkit, and maybe through that the oneAPI toolkit. Maybe you can help answer some of them.
Yeah, so I think the question about the oneAPI. So you want to have it through.
No. So I was simplifying. They wanted to. So Rudra had the question: whatever Tornado is doing, can it not be done in oneAPI, as oneAPI is two as well? So two supports CPU, GPU, and FPGA. And I think the answer is that it's being done through the Level 0 library.
Yes. Yeah. So we access the oneAPI ecosystem through Level 0, although through OpenCL, because we also using the Intel driver for OpenCL, is kind of a way to access there as well. I must mention that SPV is valid intermediate representation for both OpenCL and level 0. So in theory, we could use exactly the same kernel to be dispatched through the OpenCL runtime. Because we partnered with Intel it was the beginning of the project, and 2 years ago, and was the beginning of level 0, they kind of encouraged us to use level 0 directly. However, we have plans, we're working on it actually, to use it also with OpenCL. So we can have both the same SPV dispatched through level 0 and OpenCL. Yes.
And I think Jakob said, is oneAPI codable via Java? Like through, I guess.
I'm not aware of that, to be honest. Maybe I'm not the best person to answer, but yeah.
No,
Okay.
I think my point was just was a comment to Rutra, that
Okay.
one of the advantages of TornadoVM is all the languages that you can code it in and not have to worry about anything. And I don't know if that's the case for oneAPI or if it's maybe or how that works. So if there are a lot of Java developers out there, and for us, this is luxury, not having to really think about too much about another language or another mindset for programming the GPU and the FPGAs.
Yeah, what's exciting to me is that Tornado is giving the ability to do GPU offloading to Java essentially, right? I think that's pretty exciting, and leveraging a lot of these things like level 0 that's already there. And I think that's really. I found that presentation so compelling because there's so much Java code out there, and that now that you're able to say, yeah, I can now use all the pieces of my computer for computation is what makes it exciting, right? So if you're running on a system that's got an FPGA or you want to create an FPGA to do certain tasks, you can now enhance your current Java code to take advantage of accelerators, which is what oneAPI is too, right? But it's like reusing the architecture that oneAPI is using at its lowest level, and taking advantage of that. I think that's really great because. In my opinion, the more people who are using these lower levels and are as a dependency means that the lower levels, these like level 0, becomes more valuable, right? And the need to maintain it and be able to support new ones becomes even greater, right? So.
Yeah, absolutely. So now I just want to clarify one thing. It's aligned with what you say. So for us, level 0 makes total sense. That's my opinion, okay? Because at the runtime level, we have so much control. I think it's very appealing for system programming. For example, Tornado runtime and so on and so forth, right? Because we have so much control. I find it a bit complicated if you go up and you want to have an application that directly uses level 0 because, yes, so for that, maybe you stay with libraries in the oneAPI ecosystem that can use the level 0 or not. Another thing is that, well, it's related to one of the questions I see in the chat as well, saying that it doesn't mean that you cannot port CUDA and not, or just code Java directly. Well, I should say, okay, I want to be honest. So if you are using CUDA, there is probably not much to get from Tornado, right? Because you already have your CUDA applications running and you know your system. However, what we want to do is for non-CUDA developers, for Java JVM-based developers, still it's complicated. Why? Because as a Java developer, you need to understand the Java workflow, how Java works, etc., and so on, to get most benefit of it. And also, you're enforcing the Java developers to learn about an execution model, and a programming model that is not Java. It's totally disjoint, right? So basically, you're breaking somehow Java, and you create a dependency, right? So this write once, run everywhere is not valid. What we try to achieve with Tornado is kind of having that illusion still. So just write Java, is a subset of Java, and you can run on multiple hardware, right? Because Tornado will take care of offloading and managing the memory, managing migration, and so on and so forth. So from my view, what is kind of an obstacle for the Java community to get into hardware acceleration, maybe it's not just the kernel itself, it's everything around it. It's data manipulation, it's buffers, it's synchronization, etc. For example, I can give you the reduction case, right? If you know parallel programming, you know the reduction. How the reduction is pretty much full of dependencies, right? There are algorithms, especially I highly recommend the CUDA guideline to do reductions. It's pretty good. To split the data, get your kind of bucket reductions in groups, and then and then step by step reducing those groups. You know that on GPUs, L1 is not coherent, so you have to introduce your own barrier. So how do you explain this to Java developers, right? How is a barrier? Why memory is not coherent? Tornado will take care of that for you, right? We might not get 100% of performance, but it's good enough to get to increase performance of existing applications. That's the philosophy.
But aren't you saying that? I mean, you say good enough, but it's probably quite a bit more because you're using multiple hardware device accelerators anyway, right? So whatever you're current doing with just using the main processor, if you're doing the offloading, then absolutely this is great. You know, I mean, it's still going to be better than the default.
Yeah, so just to recap what I mentioned, so Tornado, we don't try to replace Java or JVM completely. We try to complement, and this is a good discussion we have been having in our group for many years. Still, we have these discussions. Should we support more Java features? Should we not? Should we stay where we are? Because in my view, if we use a GPU, it's because we know that center type of applications can run really fast and really efficient on those devices. So if your Java application somehow we can accommodate it or can be structured in such a way that is really usable for GPUs, let's go for it. Maybe your application doesn't follow this pattern. That's fine. We stay on CPU, right? That's totally fine. So we don't want to replace Java or JVM. We want to complement. The thing is, those specialized applications are today, in 2023, important enough to consider to have a subset that can be offloaded and can be run really fast. For example, deep learning applications, which are matrix multiply-based applications, these kind of things, right? The thing is, there are some domains so important today that make sense to have this type of sub-applications running on these devices, right? You can think about every accelerator specialized for certain type of workloads, right? Essentially.
Is there ways to use like all this things we've done in oneAPI itself in Java? But I mean, because there's no Java binding, so
there's no Java bindings. That's a difficult question. I don't know if I can answer this question. But
no, then
yeah. So I mean, we're working with Intel folks to advance this project. I think they are interested in having a Java approach to this because, as Jacob mentioned, there's a lot of Java code out there.
Yeah. I think being able to augment current Java code to take advantage of accelerators is really a kind of a next level kind of cool thing for Java. Have you ever presented it at Java conferences or?
Yes, indeed, we have. Yeah, so a couple of years ago we went to JVMLS, which is the Java conference in Oracle. basically to expose what we're doing in the Java ecosystem, try to push to move Java forward. In fact, we're going back this year in August to California as well. We have also presenting in DevOps. I can't remember now all of them. Joker conference in Russia, a bunch of them. Yes. Yeah.
Oh, okay. That's really great. Have you gotten, what kind of feedback have you gotten from the Java community about?
Well, it's very diverse, to be honest. It's depending on the needs of each Java developer. Essentially, the most common one is what is supported and what is not supported, right?
Right.
That is the most common question. Because as I mentioned, we run a subset. People are interested in which subset it is. So we have in our website and in our documentation explicitly a list of features that we support and an explanation why we don't support this. For example, we don't support exceptions, or we don't support inheritance. These kind of things that the Java users are used to, but for performance reasons, we don't want to put it on a GPU just yet. The reason is that, as you know, probably you all know GPUs even better than myself.
No.
So
I wouldn't say that.
So GPUs don't have branch predictor, right? So if you put a lot of branch in there, branchy code, you might kill performance. So we try to avoid these things, right? There are some ways, there's some research to minimize branches, etc. But by introducing all this logic that Java has, we might kill performance. So it's kind of a trade-off. Yeah.
Do you have examples of? I know you have a repo of examples, but do you have? Has anybody porting to using Tornado like that's doing something non-trivial? Is that something you could talk about? I don't know.
Yeah, absolutely. So I can give you an example with the most recent project I'm working on because I have kind of code in my head.
Yeah.
But there are plenty of them. So we're working with a company in Switzerland. It's part of the Aero EU project.
Yeah.
And they are connected to the European Space Agency. So essentially what they're doing is data analytics. Basically, it's a company that says, European Space Agency gives you this set of data sets that you need to analyze, spectrums, frequencies, and so on and so forth. And we are porting those algorithms, astrophysics, to Tornado. It's interesting because I asked them, well, why can't you use CUDA directly? And say, well, we have people that port to CUDA, but it's hard to understand and hard to maintain. I'll say, well, maybe it's not that complicated. But then I saw the source code base. This is not, I work in academia, so I'm working with academic cases, right? But this is real. And they have a lot of code just to connect it with databases on the processing on the node, then send back to duplication on the main host back and forth. It's a really complex program. Just by introducing those dependencies, they have to be careful where to put it, etc. And they used to have it in Java. So for them, if we say, well, we can accelerate it, maybe you don't get 100x, but 70x is good enough for us. Right, and that's what we're looking for. So that's why we are partnering with this company.
Oh, fantastic! Yeah, Felix gave an article on talking about branches. He does know GPUs.
Okay,
not me.
I like to think I do at the very least.
But you do when you compare it to me. So, yeah, that's great. Does anybody have any more questions for Juan in regards to anything in his talk? Or, okay, it looks like we don't have any more questions. I mean, I could keep going with questions, but it's also evening for you, and I don't want to extend it any longer than this.
Yeah, that's fine. I enjoy this, so as you can tell.
Yeah, that's good. We are recording this talk, so for I know Felix here can, and if maybe it's a
Yeah, it was in another call. Sorry about that.
yeah. We will have this recorded, and I'm hoping for next time. I'm hold on. I'm trying to get. I'm in talks with Carol Herbst to do a talk on as our next guest, where he talks about graphics drivers and Mesa drivers and SQL and so forth. So
That sounds fun.
that might be a fun, and Spear V as well. I try to get him to come because Spear V. Yeah. So right now he and I are discussing what would be a good topic along those lines, because it's not necessarily a oneAPI. Like I said, I like topics. It becomes oneAPI when oneAPI people show up. So so that's how I look at it. But so once again, thank you, and Juan, and maybe I'd love to invite you for or maybe our next step summit, and then maybe talk about the Java angle of being able to
happy to talk. Yes. Thank you very much. Thank you for all
Thank
the questions.
everyone.
Just to let you know that if you have more questions, feel free to reach me via email or in the website. We have also talks, tutorials, and so on.
Yeah, and he's on our oneAPI Discord, so you can reach him on Discord. So if you have any questions, I know Prasanna, you're on there, and Felix is. But if anybody else wants to get on Discord, there's Juan is there, and happy to talk to you there, or whatever. So, okay, all right, everyone. Thanks, and have a wonderful weekend.
Thanks.
Bye-bye.
Bye.
Thank you. Bye.